be here to give a talk on differential privacy. And this talk is based on joint work with my advisor Jin Cheng from Nanjing and Eliáš from Rutgers. The main component of this talk also appeared in Suda this year earlier. Okay, so today I'm going to talk about differentially private approximation on graphs. Okay, so why we care about graphs? Okay, as we all know, graph-related data structures are widely used in industry for modeling the user relationships. Okay, for example, in some music app, there is a bipartite graph that can be used for modeling the user preference for some corresponding artists or albums. In this bipartite graph, there is a list of users and a list of artists, and the edge weights represent the user preference to the corresponding artist. Okay, another example is a typical social network where the edge weight represent the frequency of interactions between any two friends. Okay, and in practical applications, the property for this graph that usually poses critical concern is the size of ST cards. For example, the data analyzer might be interested in how much a specific user favors a specific group of artists. For example, if the subset of vertices S includes only common and the subset T includes a list of like KP artists. So asking the size of this ST card is equivalently as asking how much does Kalman allow KP artists. And such information are naturally very sensitive. From now on, we consider undirected graph on vertices with n-weighted edges. And the maximum unweighted degree is delta. It means the maximum number of edges incident on any vertex is delta instead of sum of edge weights. For example, in this graph, the maximum degree is just 3. Okay. The most natural idea to protect privacy from any type of data analysis, such as asking the ST card queries, is to output a private copy of a synthetic graph through some mechanism M. And after you have the synthetic graph, you can learn anything you like from it. Okay, for the privacy part, we want M be differentially private. I will introduce differentially private later on. And for the utility part, we want the synthetic graph G prime preserves the calculus of the original input graph, and somehow we want a more stronger demand to preserve the graph Laplacian matrix of the original graph. Okay, let me introduce differential privacy. Okay, given a randomized algorithm, we see this algorithm is epsilon delta differentially private for any neighboring data sets G and G prime. Their output distribution is very similar, and the similarity is measured by these two parameters epsilon and delta. Okay. Okay, so in particular, if delta is 0, we see the randomized mechanism M is epsilon pure differentially private. And in this case, it is seen that the infinity norm between the difference of two distributions is bounded by some parameters related to epsilon. Okay. And if we do not specify parameters epsilon and delta in this talk, we just set them and their conventional values where epsilon is a small constant and delta is the inverse of some large polynomial in M. Okay. You can see that in the definition of differential privacy, we need to define what is neighboring graphs. In this line of work, we really use edge level differential privacy. It means G and G prime are neighboring if and only if they have a difference in one edge by almost 1. Okay. And the goal of differential privacy is to make any level neighboring data set indistinguishable for some anniversary from just reading the output, so that adversary would not easily know if there is an edge or not between any pair vertices. Is there any question about the definition of non-biasing? Or should I explain it more clear? Okay. So before we introduce cut approximation, let's consider a more general problem for spectral approximation, which has been extensively studied in both private and non-private settings. Okay, in this problem, given a graph G, we want to output a new graph G tilde such that the Laplacian matrix of G can be approximated by the Laplacian matrix of G tilde with a constant multiplicative factor and additive factor data, while preserving epsilon delta differential Python. Okay, for looking at most familiar with Laplacian matrix, we just define it as the diagonal degree matrix minus the adjacency matrix. And you can verify that the Laplacian matrix of G is symmetric and is positive semi-definite. Okay. We see it is a more general problem because once we have a approximation of the Laplacian matrix, we can use the synthetic graph we can use the quadratic form of the synthetic graph to compute the calculus. And the error can be reduced to the quadratic form. Okay, and also it has been well known that the spectrum of graph Laplacian has a relationship between many important other graph parameters such as hidden time, commute time, and count time. And these parameters are related on the simple random walk on graphs. So private spectral approximation has been noticed for a long time. It was firstly started by both Rondat and Shep in 2012, and we show that by doing Johnson-Lindersloot transformation, namely, you multiply a random Gaussian matrix on the square root of the graph Laplacian matrix, it is enough to preserve differential privacy. Because you are doing Johnson-Lindersloot, so you will have a constant multiplicative error, and you will finally have a square root and additive error on the spectrum of graph Laplacian. Later results in analyzed Gauss can also be used to analyze the graph Laplacian matrix, and so analyzed Gauss is merely just add a random Gaussian matrix to the graph Laplacian matrix. So there will be no multiplicative error, just have an additive error squared n, because the spectral norm of a random Gaussian matrix is square root n. Okay. We know that both algorithms, either adding multiplicative or additive Gaussian noise, are oblivious, that is, the noise is independent of the input. So it means that even for very fast graph, this algorithm will give an approximating algorithm with square root and additive error. Okay, but in real application, the large scale networks are usually very sparse and weighted. For example, we use Eliáš random graph to simulate a social network, and so you can imagine that the number of frames the maximum number of frames one could have, namely the maximum degree in the social network, is usually negligible compared to the total number of vertices. So So the question is, since real world graphs are usually sparse and weighted, is there a private algorithm that could achieve a better utility that is square root n than a various mechanism on the spectral approximation for sparse graphs, especially for those graphs has a bounded degree delta? Okay. In this talk, I want to present a positive answer to this question. In particular, we show that given a graph, n-vertex graph G is maximum unweighted given delta. There is a polynomial time epsilon differentially defined algorithm such that we can preserve the graph Laplacian matrix with an additive error beta, and beta is delta over epsilon. As I mentioned earlier, delta is usually way smaller than square root n, and the error only depends on the most popular one, so it is not obligation mechanism. Okay. As we already have a good approximation for the spectrum of Laplacian matrix, it is somehow very direct to use such synthetic graph to compute graph parameters related to graph Laplacian or its inverse. And one of the parameters that are particularly important in graph spectral theory is effective resistance between any pair vertices. For the who are most very familiar with effective resistance, you can consider the flow graph and the large resistance. And the resistance between any two pair vertices is the inverse of its edge weight. For example, if there is no edge between two vertices, the resistance is infinity. And the effective resistance between any two pair vertices can be computed by the inverse of the graph Laplacian matrix. Okay. A well-known fact, I just mentioned earlier, is that there is a connection between the run works on a kinetic undirected graph and the electrical network. So many important graph parameters, including real time, fitting time, and count time, can be privately approximated if we have a good approximation on the effective resistance. Okay, so based on the spectral approximation algorithm, it's somehow able to show that by giving an approximation on the inverse of the graph Laplacian matrix, we can give a theoretic algorithm that approximating all pair effective resistance with an error delta over lambda g square. Here, lambda g square is the second smallest eigenvalue of the graph Laplacian matrix. And we asked the graph to be connected so that the second smallest eigenvalue of g is non-zero. Otherwise, the count time can be infinite. Okay. To see why this is indeed an improvement, we use noise adding management and the benchmark. The error of noise adding management depends on the sensitivity of effective resistance. Okay, so we can show that there exists a neighboring pair of graphs G and G prime, such that the most sensitive pair vertices in the two graphs could possibly achieve the value of 1 over lambda G square. Okay, actually it happens in complete graph. Okay, so if you want to theoretic algorithm and use basic optimization, it will give us the error n square over lambda G square. And if you want an approximating algorithm, it still gives the error n over lambda G square, which is also very large. And go back to cut approximation. In this problem, given a graph G, we want a new graph G has such for any st, any subset s and t, we can approximate the st column with a pure additive error beta, while presuming the epsilon diagonal fallacy. This problem probably is the most widely studied problem in diagonal fallacy, and it was first asked by Doug Maxwell and Nissen Smith in 26. The two algorithms I just mentioned for graph spectral can also be used for approximating the cuts, but it will suffer an extra impact, so the error is n up to 1.5. Okay, and another type of algorithm based on private optimization. Briefly speaking, Kulkarni and Ullman show that you can approximate all ST paths on the graph with multiplicative with an additive error of rows over L1 normal W times N. Here the L1 normal W is the sum of edges. Okay. This also show that you can use mirror descent to approximate graph efficiently and achieve same error with square W1 times N. Okay. So let's compare the two types of bounds. For the spectral-based algorithm, for dense graphs, the spectral-based algorithm works better, but it does not depend on edges. But for sparse graph, if the graph is unweighted, then the error rate then the square root m error rate mirror descent looks perfect. But if for weighted graphs, the error is unbounded because the error depends on the sum of edges. So these two bounds have some discrepancies. And so it leads to another question. A weighted graph has many parameters, such as number of edges, maximum width, and the sum of edges. So which of these parameters is the correct answer to the private cut approximation? Okay. For this question, we show that given a weighted graph with n vertices and m weighted edges, there is a polynomial time epsilon delta DP algorithm to output the synthetic graph GCAT such that we can do cut approximation in error squared m over epsilon. And we also show a tight lower bound with respect to all parameters, including epsilon. Which is also square root m over epsilon. So the correct answer is square root m over epsilon. Okay. So here is the picture for private graph approximation. For unweighted graph, Eliáš and already gave the optimal answer. And for weighted graph, we show that the correct answer is not depend on the edges. Okay, for one thing I want to note is that the epsilon in the previous work is inside the square root, and the epsilon in our result is outside the square root. So if epsilon is smaller than 1, which is really the case, the private approximation on cut approximation on weighted graph has a larger lower bound, which identifies that weighted case is strictly harder than unweighted case. Okay. So let me introduce some ideas behind the bounds for spectral and cut approximation. Okay, for an input graph, it is possible that there is a difference in any entries to pair vertices, right? Okay, so a very direct approach is to add a random perturbation on any pair vertices. Usually we choose Gaussian noise because of its Gaussian concentration properties. So what we are doing is to just overlay a random Gaussian graph on the original graph, and output a synthetic graph is this. Okay. So it would cause square root n error because the spectral norm of a Gaussian random graph is about square root n with hypermobility. And somehow for general graph, this error is inevitable for the lower bound in the graph. And also the output is a dense graph because you overlay the Gaussian. So you can always to run a specification procedure after you have the synthetic graph. But somehow in some applications, the nth graph speeds to store the intermediate graph and store the vertices. So any questions on this? Okay, so let me introduce some ideas on how to improve this using the sparse input graph. Okay. Compared to adding noise to each pair of vertices, we notice that if the graph topology of the edge of the underlying graph is known to the public, the problem should be much easier, right? Because if the underlying graph is known to the public and the only private information is the edge width, you only need to add algorithms on the edge side for graph. So this, our general approach is to first select a new edge set previously, and then add noise only in the edge set. So if the graph is sparse, you only need to add a very small noise compared to overlay complete Gaussian graph. Yeah, and you can see that the error depends on the size of the hat, where the hat is the new edge set of the new underlying graph, and the output graph is sparse if the hat preserves the sparsity. So you don't have to output the dense graph as a direct output. Okay, so such general approach asks us to design a sampler that is both private and sparsely preserving. Okay. So, okay, so to sample a new edge set, that is both private and sparsely preserving. Very natural idea is to use exponential mechanism, which is a very commonly used mechanism in digital policy for sampling described candidates. In this mechanism, if we suppose we have a potential output T, which could be described, and they have a utility function which is that for any pair of neighboring graphs G1 and G2, the utility function can be defined that for any particular output it glitches up to some sensitivity. Then if we sample a candidate according to this distribution, we could have epsilon differential values on the yeah, so I want to note that the epsilon is infinity. It means there's no price, right? If there's no price, say, sampling from this distribution is exactly sampling who minimizes the utility function, right? But there's no price. If epsilon is 0, sampling from exponential mechanism is uniformly sampled. There's no information. So this is total policy. And epsilon does controls from just to the optimal line and the uniform sampling. Okay, and in our problem, the potential output is all possible edge sets. Okay, so but directly sampling from such potential outputs could be computationally challenging, because the size of T is usually exponential. And for example, if you want to sample all edge sets, it's indeed exponential, and because it's a subset of n to 2 elements, and the utility function can also be hard to compute. For example, if you want to do a cut approximation, so one possible utility function is to just the maximum error in all cuts, which is indeed computationally hard for exact answers. Okay, so to address these issues, our idea is to just use the error in L1 node and the scoring function to measure the error of each possible edge set. Okay, then we let all potential edge set to be equally sparse. Okay. Formally speaking, given an integer that is m, where m is the number of edges, we sample from all underlying graphs with exactly k edges according to this distribution. Okay. So S in 0, 1 up to n to 2 is a possible edge set, and we just constraint is set in exactly k, and we sample it according to the distribution and in this equation.
Zongrui, what does it mean for the error? The utility function to be the error in that one norm?
I just going to explain it.
Okay, sorry.
So I'm going to answer the first question. Okay, if we define the G on S with the induced graph of G on the edge set. Okay, for example, if this is the input graph and this is the output edge set, and this new edge set just distorted this edge, right? And it has a new edge with here. So if we consider the original graph as a vector of n to 2 dimensions, and the new graph also a vector of n to 2 dimensions. So this utility function can somehow be written as G minus G on S, which is the sum of edges that is overlooked by the right set. Right? So for example, in this case, the value of the utility function is just W4. So intuitively, if more edges is overlooked by the right set, it will suffer more penalties. Okay, we remarked that this distribution looks like a product distribution, but it's actually not because of the equality state constraints, and also because this constraint the support is non-convex. Okay. So luckily for this distribution, we show that given a power budget epsilon and an integer smaller than n and is equal to 2, we can set there is a polynomial time algorithm we want to implement n squared and samples that are extract exactly from this distribution. Here I'll briefly sketch how to design such a sample. Okay. Now consider an input graph. We assign each pair of vertices with a polynomial random variable, no matter if there is an edge. And the probability of such polynomial random variable being 1 is defined as this value. So if there is no edge between like the two pair of vertices, the probability of being 1 is just 1 over 2. Okay. Then we just consider sample each polynomial random variable independently, condition on then the non-zero elements in the output is exactly k. The reason we can do that is that we can immediately verify that this is exactly the distribution we just mentioned. Okay, now we can expand this probability as a product of n to 2 different conditional probabilities. It's just the chain rule. Okay, so this form of product probability naturally implies an algorithm sample from it. Okay, so if you want to sample x1, you just need to sample according to its marginal probability condition on non-zero elements of the output is exactly k. If you want to sample x2, it depends on the output of x1. If x1 is 1, when you sample x2, you need to sample according to its marginal probability condition on that the elements, the last n minus 1 elements has k minus 1 elements. I have k as one, k minus one non-zero elements. And if the value of x1 is 0, you sample x2 according to its manual probability, where the last n minus 1 element has exactly k non-zero elements.
These Bernoulli's xi, they are just like the same thing that comes out of a randomized response, right?
It's randomized response. I'm not sure. I'm not sure it's equivalent to randomized response, but it's just some. It's probably indeed depends on epsilon. Any questions? Okay. So generally speaking, when we want to decide the edge E, if S edges is chosen before E, we can write its marginal probability explicitly, and we just need to compute this equation to decide decide its marginal probability. Also, actually, this is not very easy to compute because you don't know you don't know the value of like the probability of elements from I to N has exactly two non-zero elements, but fortunately we can compute it recursively. So somehow it will give you n square times k polynomial algorithm to compute all these things, and you just sample each variable one by one according to its model. Okay, so with the topology sample I just introduced, we now have algorithm for spectral approximation. First, for an input graph G, we perturb the number of edges. It's random variable from the Laplace distribution, and get n hat. Okay, so then we run the topology sample I just introduced on the input n hat and G. So it's just you sample it does mean that you sample a new set of set n hat on the input graph. And finally, you need to relate your edges only in your edge set. You just mention you just sample, and it gives you an undirected graph G hat. Okay. So note that we make sure n hat is at least m with probability at least 1 max theta. It seems that this probability 1 max theta, the new edge set will possibly cover the original edge set. Also, by carefully setting the parameters, we make sure that the algorithm preserves the sparsity of the input graph because m hat is will be not very large compared to m. Okay, so we just saw the algorithm for spectral approximation. The priority of such algorithm is very derived from basic computation. Okay, so for example, we just show that this algorithm is this part is coming from exponential mechanism, if you remember that. And the first and the third step is private for the follows on very standard mechanism, which is Laplace mechanism. Okay, so the privacy part of this algorithm is very direct, and so I want to introduce some ideas behind the utility guarantee. Okay, so I just mentioned that the topology sample can somehow be considered as an exponential mechanism, but it's L1 norm and this scoring function, but a small error in L1 norm does not give me anything on the spectrum. So if we want to have a spectral approximation, we probably need to use more properties of the topology sample law. And the first observation is that if the input graph has maximum degree delta, then the output graph or the output of the sample will also have a maximum degree around delta with high probability. The intuition behind this lemma is that the condition of whatever edges is choosing in the edge set. For the edge, for the vertices that has no edge, then the total sample will assign them equal probability of being chosen, because they have same weight zero. So the probability of being chosen for this vertices is equal. Okay. Under this observation, we can see that our condition of k edges is chosen in E. The distribution for all vertices that has no edge in the it's somehow like a random graph model where you choose n has minus k edges uniformly from this area. Okay. So to study the concentration of the degree of such random graph model, we could use a simple coupling argument to reduce that graph to the standard GM random graph, which samples m hat minus k edges uniformly randomly. And then we use a standard reduction given by Fritz and Kronsky, which seeing that if n is large enough, then for some graph property p, then it's monotone increasing. The behavior of GM random graph is very similar to GMP random graph. Okay. Okay, so we just let the probability P be that G has maximum degree larger than delta. This is the monotone increasing probability because after adding an edge, the probability remains to be true. And with this lemma, we could reduce the GM random graph to Eliáš random graph, which sample each edge independently with some probability. And the concentration, what is this? The concentration of the degree in the Eliáš random graph is very direct. So it is seen that the maximum degree in this GM random graph is also concentrated around delta. And it also implies that the maximum degree in the output graph of the total sample will not exceed hotel delta plus delta. The second step is to show that as in additive or reverse mechanism, such as adding Gaussian noise or Laplace noise, the error on each edge is at most log n. Briefly speaking, you can derive this by analyzing the edges that is incorrectly chosen by the sample and incorrectly removed by the sample, and show that they both have small error in edge weights. Okay, so these two things just seeing that the difference between the input and output graph is a random graph with maximum degree delta, and the maximum edge weight is log n, right? So this random graph, the spectral norm of the Laplacian matrix of this random graph, it should be square times logarithm of n, right? And so this is why that's why this algorithm gives us delta times logarithm n error on spectrum. Any questions? Actually, I don't know if you are familiar with spectral graph theory, so if you have any questions, just interrupt me. Yes, so now I will introduce some intuitions behind the cut approximation. Okay. Using the spectral approximation as a black box will give a algorithm on cut approximation with error delta times n, which is not optimal. Okay, to get optimal bound, we will explore some some default properties of the polysample. Okay. Note that in the algorithm for spectral approximation, if an edge is not chosen by the topology sampler, then we just set the width of these edges be 0. Okay. However, instead of just remove these edges, we can use another approach to better handle the edges. Generally speaking, we could use the topology sampler and the private subroutine that automatically split the graph into 2 parts. And one part is the edge is chosen by the topology sampler, and the part is the edge that is discarded by the sampler. Okay, so further we have 2 observations. The first observation is that if an edge has width larger than log n, then it will include it in the outputs for example, this hypothesis. The second observation is that the topology sampler preserves the spot state, that is, at most m edges in the outcome has non-zero width. So since there are at most edges, if there are at most m edges has non-zero width in the output graph, as the input graph has also m edges. So it is seen that in both subgraphs, they have they have at most m edge, at most all m edges which have non-zero width. Okay. So the about 2 facts is just saying that this subgraph that is discarded by for example has at most m edges and the edge width is at most log n. Because if there is an edge width that is larger than log n, it will be here. Okay. If you remember that in the first work on private realism, if the input graph has a bounded has a bounded maximum, has a bounded sum of edges, then the error is very small because the error depends on some edges. Okay. So this, okay, the final observation is that if the topology is public in this graph, then approximating the cut by just adding the orthogonals on the edge side already achieve optimal errors. Okay, so these 3 observations gives us the algorithm. For the subgraph is bounded sum of edges, we just run private realism on it. And for the graph is public topology, we just add a random conversion only in the edge set. Okay, so we call that the error is private realism is square root W1 norm times n. W1 norm is some address. Okay, so it means that for this subgraph, the error would be square root n. So yes, for the primary distance slope, the error is sort of n, and by the concentration of combination of approximates, we can also show that in the second subgraph, the error is also square root n. And combining these 2 subgraphs, we can show that the error on also all ST cuts in the original graph can be approximated with additive error square root m, which is the optimal error we can achieve. Okay, so so far we talked about some ideas behind the cut and the spectral approximation, and the sample results in polynomial time n squared k. Okay, it is a polynomial time algorithm, but somehow it is not good enough. The reason I say it is not good enough because that in some profit-driven companies, the analysis of large-scale graphs is usually implemented in a non-price way, because if you run a private algorithm, you will suffer much more consumption on time and space. Okay, so for example, for this algorithm, if we want to explicitly sample side, we have to compute the marginal probability in advance. So So it's very unlikely we can do better than n square or n square times k time if we want to exactly sample from this distribution. So the question is, if we allow approximate sampling, could we do faster than n square k or n square time? And the ultimate goal is to output a topology sampler in just in linear time, because in non-prior setting you just read the graph and output all plus y theta, which is a linear time algorithm. Okay, and I want to show that the answer is yes. If we allow multiplicative sampling, we can actually sample from this distribution in almost linear time, which is all the n. Okay, so and the solution is through use MCMC method. Here MCMC means Monte Carlo. Okay, so I assume you know about the Markov more or less. Okay, from now on we consider a range of stochastic process where the state space is just a reversible access, which is a set outside of N2. Yeah. And you can imagine this stochastic process. The initial element is the real access E in the original integral, and we construct a process where each time t there's new access, and the distribution of the new access only depends on the distribution of the previous access. So it's actually a Markov chain. Okay, hopefully when t is getting larger, we want the distribution of xt is getting closer to the distribution we mentioned. Okay, when it happens, that is, if the distribution of xt is very close to it, we can just output xt, and it gives us an approximative algorithm. So the next question is how to construct such stochastic process. Okay, so here we consider a well-known Markov chain called basis exchange work. In basis exchange work, we are giving a description of the distribution pi over the subset of over the set k subset of big N, and the output is some subset. Okay. So the basis exchange work goes like follows. First, we initialize some arbitrary subset x0, such that the non-zero elements in x0 is k. And in each step, we just remove an element in this subset uniformly and random. And then, according to the input distribution pi, we sample a new access that outside the current state according to the marginal probability. And we just add it to xt prime, and it gives us the new state xt. So okay, now so now we put the basis exchange work in the context of our problem. Okay, we can consider such stochastic process. First, the x0 is just the access or the underlying graph of the input graph, and also we uniformly at random remove an e, and we get x1 prime, and then we just sample an edge in the outside x1 prime according to this distribution, which is proportional to E up to epsilon times WE. WE prime, where WE prime is the weight of the prime. And we add this edge to the epsilon prime, and we got a new access. And just go over and over again. Each time we will have a new access. And okay, there are two facts about such about such stochastic procedure. Okay, first, it is very easy to show that when t is infinity, xt is the distribution is a distribution path. And the second fact is not very obvious. It's seen as it's seen that this such markup chain process is actually convergent very fast. In particular, when t is linear and almost linear in k, xt and x infinity has total conversion distance smaller than delta. Whereas the dependence on delta in the mixing time is just log over delta. You can derive this factor from the only log-concavity of the distribution I just mentioned. Okay, but this is not the single topic of this talk. So. Yes, so anyway, we can use a markup chain to give an order k time approximately sampling mechanism and sample a size k subset of eventual elements according to this distribution. So this is actually gives almost a linear time approximation on both spectral approximation with similar rates. Okay, so finally, let me do a brief summary and share some interesting open problems. Okay, in this work, we give a new algorithm and with a new bound on the graph spectral approximation, and this algorithm is pure differentially private. And we use one of the subroutine of this algorithm to give optimal bound on private cut approximation for general graphs, which is called m-over epsilon. And for general interest, somehow the Toveri sampler is very genetic and can be used in other scenarios instead of only for graphs. And there are some interesting open problems that you might be interested in. First is for optimal spectral approximation. We believe that the delta over epsilon error is not final. Somehow we conjectured that the optimal error should be delta square root delta over epsilon. So the question is there a DP algorithm that achieves such error rates in spectral approximation? Okay. A more interesting question is about cut approximation with modification error. The algorithm I mentioned it gives a purely additive error, which is third and but like a decade ago, Blocky and all showed that there is a double exponential time algorithm that achieves n over epsilon additive error if we allow multiplication error. Okay, so the question is, if we just allow multiplication error, is there an efficient algorithm that achieves same error rate, which is n over epsilon on cut approximation? Okay. I think this is all I have to share.